Hi everybody, welcome to this R tutorial on social network analysis. Today we are going to cover a bunch of stuff. We'll look at the basics of network analysis. We will build our first network using iGraph library. Then we will calculate some key network metrics to help us understand the network better. Finally, we will figure out how to detect communities in a network. This is all really cool stuff, but before we get into it all, let's look at the what of this whole situation. So first of all, what is network analysis? Well, a network is a set of objects that are connected to each other. For example, train stations that are connected to each other via train lines, airports that are connected via airlines or flights, people working in the same movie together or people working in the same organization. They are also an example of network. Now, when we analyze these objects that are interconnected and the interconnections between them, that is network analysis. Now, with that as an introduction, let's just get into the code. But before we do that, if you find this video useful at all, please don't forget to subscribe to my channel and hit the bell icon. Let's get into the code for doing some network analysis. We're going to start by loading the library iGraph. Then we're going to load this data set that we have. It's Game of Thrones Season 1. Let's examine this data frame here. This is a data frame with information on interactions between different characters. So Ned and Robert interacted with each other 192 times. John and Sam interacted with each other 121 times. So this data frame here is very typical of how you need the data to look in order to do some kind of network analysis with it. So you have node 1, node 2, and some attribute about the relationship that may or may not be present. So this is always your starting point. So now let's go back to the code. I'm just going to do a little bit of coding magic here to change how these names are written so that they look better when we plot them. Then we're going to turn our data frame from a data frame object to a graph object, and for this we use the function graph underscore from underscore data frame. And now let's just examine the iGraph object. So this is the kind of information that you get. So this is how the nodes are represented as edges. So Ned has a relationship with Robert, Ned has a relationship with Littlefinger, so on and so forth. To look at all the vertices or the nodes, we can use the function capital V. So there are about 127 vertices here. So if we want to look at the edges, we use capital E, pass the iGraph object to it, and we see all the edges. So there are about 550 edges here. Now let's go ahead and quickly plot our graph, and so we use the function plot G. And this is how our network map looks, and it looks pretty cluttered to me, but thankfully you can add a bunch of specifications of how you want your network analysis diagram to look, and you can add things like vertex label font family, and we specify it to be Verdana. We can also change the size of the label. We can also change the vertex size. We can make it smaller than it is so that it looks a little bit better, and then we can specify the layout, which is how we want the data to be presented on the sheet of paper or on the screen. So basically this uses a bunch of algorithms that allow you to specify how you want the nodes to be placed on the chart, on the network map, and this allows you to create a prettier picture than if you were to just randomly plot your network. So let's see what this looks like. So this doesn't work. Let's go with something I've already tried once. So this is how it looks. It looks pretty nice. Let's try a different type of layout. So this layout option is based on Kamada-Kawai algorithm taken from graph theory, and this is how it looks. I quite like it. So now we could just quickly add a bit of code here to make sure that we can see all these graphs together. So I'm just going to copy a little bit of code here and just run this bit again. So now you really will have an opportunity to compare the three different types of networks. If you just remove the labels, it'll be easier for you to see. However, being able to look at the picture will not give you the clear understanding of what's going on in the network, and for that you can calculate certain metrics. One of them is degree. So when you calculate degree, you can see how many other nodes is a particular node directly connected to. So NED is the most connected node here and has 57 and is connected to 57 nodes. You could also calculate things like betweenness, and what betweenness does is it tells you how many times does this particular node fall on the shortest path of two different nodes. You can also calculate closeness centrality. What closeness does is it takes the sum of the distance of one node to all the other nodes in the network, and it allows you, and it then takes the reciprocal of that, and so it gives you a number which tells you how close this particular node is to the other nodes. And so when you do this, you're able to figure out how important a particular node is in the network. So you're able to see the relative importance of a node vis-a-vis the other nodes. So now if we are to just look at this particular bit of code, and if you want to make some changes in it to reflect these different metrics that we have just looked at. For example, if I want vertex size to be in line with the degree of the particular node we're looking at, we can do that. So I've just replaced vertex size with degree of G. So it'll just calculate the degree for each node and then change the size of the node in accordance with that. I'm just going to quickly remove the vertex label so that you can see this more clearly. So I'm going to just say vertex dot label equals to NA, and that should remove all the vertex labels here. And now you can see all these different nodes are overlapping each other. So now what we're going to do is we're going to simply multiply this with a number so that the size becomes smaller than it is, so that it's just a fraction of the size, and it still signifies the relative degree. So now this particular chart, as you can see, the data is clearly represented. You can see the different nodes, and you can also see which node is more important than the other. Similarly, you can also change the width of the edges. So for that, we're going to use a metric called edge betweenness, and we're also going to multiply it with a number to be able to see it very clearly. So this is how it looks. If you just multiply it with, let's say, a smaller number, that will help us even more. And so this is how it looks. So you can see there are a few nodes here, and the relationship between those nodes are more important than the others. Now if I were to just take a part of this whole graph and not the whole graph to be able to study some nodes that are more important than the other, then I can use a function called induced subgraph. And in induced subgraph, all I need to do is pass my graph object and then specify the condition that I want my nodes to meet. So I want to include only the nodes which have degree greater than 7, and that will give me a smaller a smaller set of nodes, and I will now go ahead and plot those nodes. I'm just going to copy it here. And I'm just going to go ahead and run this. And so this is what it looks like. Fewer nodes, and we can see them more clearly and see what's happening in the network amongst the more important members of the network. So now if I were to, just last function that I want to demonstrate to you is tkplot, where I will just pass this new graph object core, and this will quickly run, and you will be able to see how you can create an interactive network. And let's say I want to select all the nodes and I want to color them all yellow. So this is what they look like. And now I just want to change the layout. Let's just say I want Fructoman Rain Gold layout. And so this looks different. Then I can have Kamada Kawaii. So these are the different layouts I can try, and then I can export using PostScript.